ladies and gentlemen, your class recording has begun. So, I asked you to take a couple of minutes and use the first section of chapter 14 in your book to fill in this outline, or this flowchart. This flowchart goes through and talks about the main terms and concepts at the beginning, and is really a good way to start this unit. If we understand these terms and concepts, we're going to have a good idea going forward when we start applying these terms and concepts. So we're actually going to start on the right-hand side of this flowchart, going this way. So, waves do what? Waves carry what? Energy. Right? From that standpoint, this section on waves builds on the concepts that we talked about at the end of the last unit when we talked about heat transfer and the ways that heat can be transferred. So we talked about 3 ways that heat can be transferred. Do we remember those 3 ways that heat can be transferred? Radiation, convection, and conduction. Okay? So, the next part of this flowchart describe 2 of those ways that heat is transferred. Here, we talked about those terms in the context of heat transfer, transferring heat energy, but we can transfer any kind of energy in that manner. So, waves carry energy through matter. That would be an example of what type of that heat transfer. Let's go with conduction on that one, okay? And we'll see why in a second. Oh, I thought you said convection. I'm sorry. Okay. All right. So, when waves carry energy through matter, that is like conduction. There needs to be something for that energy to transfer from this thing to the next thing to the next thing to the next thing. But waves can also carry energy through what? Through space, right? Another way that we could talk about this, we could also say that it can carry energy through a vacuum, right? The idea being that if something is space or if something is a vacuum, there's no what? There's no matter. It's just empty space. There's nothing there to carry the energy, but energy can still transfer through that. And most of you picked up on this, right? That would be just like we talked about with radiation. Okay? So we see here that this section with waves is talking about the context, or talking about the mechanics of how does conduction happen, how does radiation happen. I can't show you this up on the board because I don't have an electronic copy of your book, but if you would turn your book to page 459. Page 459. So page 459, up at the top, shows you a series of little masses, and those masses are hanging from the ceiling by a spring. And I think most of you would probably, see here that the red mass, 459, that the red mass that's on the far left, in the first picture, in the top picture, the hand pulls that mass downward, right? And when you let it go, that red mass would then bounce up and down, and then it would bounce back and keep going up and down and up and down and up and down. Okay? But in this specific example, the red mass is not on its own, right? It's connected to that blue mass through another little spring. And then the blue mass is connected to the gray one, and the gray one's connected to the green one, and the green one's connected to the purple one, right? Et cetera, et cetera, et cetera. So even though the hand causes the red mass to move, I think all of you could probably picture in your head that even though the red one started moving, all the rest of those would be moving as well, right? They would eventually end up moving as well. But eventually, at the very end, what would happen to all of those masses? They would slow down and stop. And then Dunphy, where would they end up after all of them are done bouncing up and down? Right back where they started. Okay? So So even though the hand created a disturbance in one of them, and that disturbance was then transferred to all the rest of them, eventually they all end up right back where they started. Okay? And that's the gist of how a wave works. So, if you go to your outline, real quick, right? Waves are the motion of a disturbance, not the motion of matter. That could be a little misleading because when a wave goes by, things move. Yes, that's true. But eventually, they will end up right back where they started. In most cases. There's some cases where that doesn't happen. Those are specific cases. But in most cases, that happens. As we just established, right, waves carry energy from one point to another. But no matter is moved. So waves carry energy, but they don't carry matter. Right? Just like we talked about in that picture on page 459. The disturbance that was created by the hand is carried from red to blue to gray to green to purple, but eventually they're all going to end up right back where they started. The last part, in order to get this wave started in those masses that are on page 459, what had to happen? Work, right? Dunphy, in order for work to occur, what does there have to be? You remember 2 requirements for us to do work. Got some help?
Yeah.
Andrew, you got anything?
Energy.
And work is energy, but
yeah.
in order for that to happen,
Force
you need force and movement or distance, right? So that hand will come in and do work. We need some kind of a disturbance, and that wave transfers the energy of the disturbance. Number 1, underneath, on letter C, there's a line missing. I apologize. I keep forgetting to fix it. So a disturbance is needed to cause a wave. But for number 1, that disturbance needs to do work. Work needs to be done. A wave is created by work being done. In the case of that picture on page 459, the work is the hand pulling down the red mass. If we talk about on the playground, so I know you guys go to the playground all the time, right? You know, right? You play that little game with the jump rope, where you put the jump rope on the ground and you like shake it like a snake, and people have to like jump over it. You know, I don't even know what that game's called.
What's the snake? It's called Snake. I swear.
It's called Snake.
I hate that game. You know what game I hate? Red Rover.
Red Rover.
Oh, I hate that. There was a kid named Michael Maroon when I was in 1st grade, and I was running over from Red Rover, and he just opens his arm, and I tripped and fell.
All right, so
The devil.
one of your objectives, one of the objectives that I wanted you to get out of today's lesson is to compare and contrast the mechanical wave and electromagnetic wave. We just did the comparison part. Mechanical waves and electromagnetic waves both do what? Well, they're created by work, but what do? Transfer energy, right? So that's the comparison part. Now let's do the contrasting part, right? What makes a mechanical wave different from an electromagnetic wave? John. The mechanical wave needs a medium, but an electromagnetic wave doesn't. John, what's a medium? Something that the wave goes through, and that medium is matter. Some matter that the wave travels through, right? So, going back to our little flow chart, right? Here, this would be mechanical, right? There are 2 types of waves, mechanical and electromagnetic. Mechanicals require a medium to travel through. Electromagnetic waves don't need a medium, right? So, no medium is required. Okay. So that's the first part, electromagnetic, mechanical. Now, your second objective for today was to compare and contrast a transverse wave and and a longitudinal wave. So, Trey, what's the comparison?
I don't know.
How do they compare to each other? Let's start with that. Well, on the flow chart, what are they both underneath? Right? On the flow chart, transverse and longitudinal, right? They are both mechanical waves, meaning that transverse waves and longitudinal waves both require what?
Matter.
Matter to travel through, a medium to travel through. But, Trey, they are different. How?
A transverse wave, particles vibrate perpendicular, while longitudinal waves, particles vibrate parallel.
Perpendicular, and then letter E is parallel. Okay? So, real quick, just a visual example of that. Okay? That picture back on page 459. That picture back on page 459. The disturbance, the wave, travels across the page from the left-hand side to the right-hand side. Or, if we go to maybe like this picture right here, right? This wave, this disturbance in the rope travels from left to right. But if we looked at the rope itself, what is this rope? Which way does the rope itself move? If we like put a little dot on this rope right here, okay? We would see this dot, and it would go up and it would come back down, but where does it end up? Same place that it starts. So the medium is moving up and down while the wave is moving side to side. Okay? This is an example of a transverse wave, where the medium moves up and down as the wave moves side to side. On the other hand, this picture right here is an example of a longitudinal wave, where we squeeze that slinky together and we let it go, and we would see the slinky sort of like contract and expand and contract and expand and contract and expand, where it's moving side to side as the wave moves side to side. We'll detail this a little bit more tomorrow, and we'll fill in the back of that outline tomorrow as well. Okay?